Okay, today we're going to work on the side splitter theorem, which is going to piggyback on our similarity information for triangles. And so at the top I have a picture here, and then we'll go through the proof. It says, if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. So if you guys look up to the diagram here in the middle, these two lines, R to S and X to Y, those are being marked as parallel, and so it's going to cut the sides in proportion. So they wrote this X over R, so this little piece, or sorry, XR over RQ, so down that side is equal to YS over SQ. Another way you could write this, we could do QR, that little segment, over Rx would be equal to QS over SY, just two different ways to write it. But basically down the side where that parallel line splits, those are going to be in proportion. So I just want to walk through the proof with you guys real quick. So this is that same diagram, but added into it, we got a couple of numbers here. So in the problem, I have taken a second and I have separated these two triangles. So here's the QRS. So this would be angle 3 and angle 4 in that diagram, and this is 1 and 2 in that diagram. So hopefully you guys see those parallel lines in that original diagram there, and also in this one with those parallel lines. Hopefully you guys will automatically remember, if we have parallel lines, that we are going to have corresponding angles that are congruent. So angle 1 and angle 3 would be a set of corresponding angles, and same argument for angle 2 and angle 4. Those are another set of corresponding angles, and then both of these triangles together share angle Q, so actually we have all three sets of angles there in both triangles being congruent. So for sure we know they're similar. So I'm going to write down here angle 1 is congruent to angle 3 in this proof. They gave us the parallel lines, excuse me, and angle 2 is going to be congruent to angle 4. This is just talking about if we have parallel lines, then corresponding angles are congruent. I probably wouldn't have written that whole sentence out, but there you go. Okay, now if you guys look to where I separated these, angle 3 and angle 1, angle 4 and angle 2, we know, even though they're different sizes, the two triangles here are going to be similar. So this is what the next step says. These two triangles are similar, just that angle similarity. Okay, now if these sides are similar, I'm just going to go through here real quick and mark up what I'm going to use. Those sides would correspond to each other. And sorry, I'm trying to grab a different color. These two sides would correspond to each other. So those have to be in proportion. So what I'm going to write down next is that those sides are going to be in proportion, not congruent, but they're going to be in proportion to each other. So I'm going to say XQ over RQ has to be in proportion or equal to YQ, that side there, over SQ. Okay, now to do the next step, I just need you guys to look back at the original diagram. Okay, so here in the diagram where the triangles are together, what's going on in this next step? They're going to say XQ, that whole side, is the segment XR and RQ added together. Same thing over here. This is what's in step number 5. YQ, that whole side, is this piece, which is YS plus SQ. So we're just adding these two pieces together. So that next step in the proof is just using segment addition. Okay, now what we're doing from step 5 to step 6 is we're kind of combining step 4 and step 5. So they're going to say, okay, XQ is equal to those two segments added together. All right, so they're adding that, and they're basically, we're taking what I wrote down in step 4 here, and we're just putting that in place of XQ q on the top of that fraction. And then same thing here, yq, they're taking what I did in step 4, they're just replacing that. So this is just substitution, what's going on, basically combining step 4 and step 5 together. And then the last step is actually to prove the side splitter theorem, which gives you xr over rq, ys over SQ. And you're probably like, where did they go from this? And the proof I had here, it's a property of proportions, but let me show you over here just real quick why this works. All right, if I divide something, I have XR plus RQ over RQ. Now what's happening here? You can't just cross out things when you have adding and subtracting, but I can separate this into two different fractions. All right, so I'm adding these together. So I'm just going to show this to you. I'm just taking the numerator and separating it into two different pieces. So XR is being divided by RQ, RQ is divided by RQ. Same thing over here. YS is over, SQ, and SQ is over SQ. So here's how this works. RQ divided by RQ here, this would just become 1. This would also become 1. And if I subtract 1 from both sides, it's just going to cancel out. And what we'll be left with is what we have over here. Just the XR over RQ is equal to the YS over SQ. So that is why the side splitter property is going to be working for us. Okay, so now that we have the proof, we can just use this. So here's your two parallel lines. Down the sides, you literally in proportion. So I'm just going down the same side. So I'm just going to do 8 over 10 has to be in proportion to 6 over x. And then we're just going to do a quick cross multiply. So I'm going to do 8 times x is equal to 60. And this is not a nice number, so I'm just going to grab my calculator here right on the screen for you guys. So I'm just going to do, let's see, 60 divided by 8. And so x here is going to be 7.5 to keep that in proportion. All right, I'm going to pull this to the side over here so you guys can see it while I do the other problem. Okay, now here's the other problem. So just take your parallel lines. We're just going to go right down the same side and put those into a fraction. So this one will be a little more complicated because I got a couple different variables. So I'm just going to do a over a plus 4 has to be in proportion to 12 over 18. We're going to cross multiply here. 18 times a. Now, remember, if you got a couple terms, don't forget to put that in parentheses when you cross multiply here. So we're going to have 12 times a plus 4. Just do a little distributive property there. This is going to be 12a. 12 times 4 is going to give you 48. And then I'm going to subtract 12a. We're not going to need the calculator for this one. And get all my variables on one side. That's going to be 6a is 48. So then a is going to be 48 divided by 6, which is actually 8. All right. The next diagram, sorry guys, this didn't come out real well on the copy, so let me just, I'm going to write over the given information there. It's not the easiest to see. This is very similar to the one we just did. We've got our two parallel lines here in that same triangle. And so I'm going to use the side splitter theorem just down the same side. So I'm going to do 12 over x plus 1 has to be in proportion to 9 over x. And again, we're just going to cross multiply here. Now, if I got two terms, I've got that x plus 1. I want to do my distributive property. And then 12 times x. So this is going to be 9x plus 9 is equal to 12x. And I would subtract 9x from both sides there. And I'm writing a little bit too big here, but I'm going to end up with 9 is equal to 3x. And so x, if I divide both sides by 3, is actually going to give me 3 as my answer. Okay, so now I have underneath here, this is just a little corollary to the side splitter theorem. Corollary just is kind of like an extension of the theorem. So the side splitter theorem requires you to have parallel lines within a triangle set. corollary here just requires you to have parallel lines that intersect a transversal. So here's what this says. 3 or more, so I've got 1, 2, 3 lines, they have lowercase a, b, c, intersect 2 or more transversals. In the diagram here, I have a transversal here. I don't really have a label on it, and maybe we'll call this L and I'll call this M just for the sake of the theorem there. So these two lines would be your transversals, what I just labeled with the L and what I just put with the M. Those are transversals. Okay, so if we've got these parallel lines cutting off these transversals, then segments intercepted, so where they intersect, they're intercepted or touched by those lines on the transversals are proportional. So let me just kind of see over here, like it says AB, that would be that segment right there, over BC, which would be this segment here, is going to be not equal to, but in proportion to WX over XY. So down the same side, and then these are split by these parallel lines here. So here's these parallel lines making these segments. So similar concept to the side splitter theorem, it just doesn't have to be in a triangle. So just here's a little one with numbers just to let us practice this. So just going down the side of the transversal here, 4 over 6 has to be equal to 5 over x in that diagram. And we're just going to cross multiply there. So 4x is going to be equal to 30. And I know that's not a nice number, so let me grab my calculator here. And I'm just going to take and divide 30 by 4 so you guys can see that. And that's actually 7.5. So that's how the side splitter corollary works. It doesn't have to be a triangle, it can just be parallel lines. Okay, so in this diagram, if I want to find x or y, this actually has the parallel lines going vertically. Okay, there's different ways you can do this. And the parallel lines cut off proportional segments, and you don't have to use all 3, you could just use 2 of the parallel lines. If I was doing this problem, I would tell you, I'm just going to highlight the segments here real quick that are cut off by the same parallel lines. So those 3 little segments, the x, the 15, and the 16.5, those are cut off between the same parallel lines. And again, these are not congruent to each other, but they are in proportion. So right down this line here, I could do x over 30, and then equals 15 over 26. See how in my proportion the 30 and the 26 are lined up in the same part, the x and the 15 are lined up in the same part. If I was going to find y there, I would actually just, I'm going to use the 15 and the 26. Again, 15 over 26 has to be in proportion to 16.5 over y. And so for both of these, we could just cross multiply. So for the x, if I do my cross multiplication there, we're going to do, let's see, we're going to do 30 times 15, and then we're going to divide that by 26. Whoops, not 264. Okay, so x is going to be, let's just go ahead and round that to the nearest tenth since that's not a nice number. Let's say that's going to go about 17.3. If I'm going to find y here, what I'm going to do, let me clear that out. We're going to take 26 times 16.5, and there we go. And then I'm going to divide that by 15. And so this is a little bit nicer decimal here, 28.6, and I'm not rounding anything there. Okay, so let me come over here. And again, I'm just going to kind of highlight the little segments that are cut off by the same parallel lines. And I don't have to necessarily have these segments be connected when I set up these proportions. Move the calculator out of the way there. And there we go. Okay, so here is how I would find x. I would just do 6 over x, and then I would do 5 over 12.5. Those are cutting off the proportions with the parallel lines. If I was going to do y, I would actually use what I have colored in green and purple. They don't have to be connected. If you have any sets of parallel lines running into transversals, they cut off segments that are in proportion. So what I can actually do here for the y, I could do 6/9 as long as those pieces are the same, and then do 5/y to get a proportion there. All right, so I just pulled up my calculator. So we're going to have 6 times 12.5 and 5 times x. So I'm going to do 6 times 12.5. Maybe I'm going to do 6 times 12.5. There we go. And then we're going to divide that by 5. So over here, x is actually going to be 15. And for the y, we're just doing this. We're going to do 9 times 5 equals 6 times y. So 9 times 5 is 45. And then I'm going to divide that by 6. So that must be the number of the day today. Y is going to be 7.5 there. Okay, now this last one is a little interesting, and there's a couple ways to do it, but probably the easiest way I can tell you to do this. You have this whole side here between these two parallel lines is 25. And then you have this z that is right here. That's our variable in that situation. Here's what I would tell you. The 12 and the z, those are cut off by the same parallel lines. Now the 25 is that whole side. So what I can actually do here, let me come down. I have enough information to do this. So on this transversal, between those same two parallel lines that cut off the 25, that entire segment I can figure out by actually adding the 8 and the 12. So that would be 20. And you can actually use that to set up your proportion. As long as the sides you're working with are cut off by the same parallel lines, you can do that. So like for this one, this transversal here, I'm going to do 25 over z. And then for this transversal, I am going to do 20, that's that whole thing, over 12. And then we're just going to cross multiply. They're in proportion as long as they're cut off by the same parallel lines. So for that one, I'm going to grab my calculator here again one more time. So for this cross product, we're going to do 12 times 25, and I'm going to divide that by 20. So my answer here is going to be that z is 15. And you could go from there. I know it doesn't ask you this in the problem, but if z is 15, we could also figure out this segment from that, if that is going to be 25, and that would be 10. And if you wanted to go back and check, we could do like 10 over 15 equals 8 over 12. You could check it that way. It's totally up to you.